Alright guys, so the first problem, we have an open box of maximum volume to be made from a square piece of material, 32 inches on a side, by cutting equal squares from the corners and turning up the sides. So just like our warm-up problem. So right here I have a square sheet of paper. We're cutting out the corners just like we did in the warm-ups. The only difference from the warm-up is that now it's an actual square sheet of paper to start with. And these squares that I'm cutting out are of equal size. So when I fold it up, once again, we get this kind of shape. Alright, so we get this folded up sheet of paper that ends up creating this kind of box. So the question is, what should be the size of those squares in order to get this to be maximum volume? So hopefully you started by drawing a picture. So we start with the square. This was 32, this was 32. Okay, so Haley, I heard you guys talking about some things. So how did you start the problem? Okay, so you knew you were going to take out these little squares. And what did you call those? You can call them x, right? So they're x by x squares. All right, so we know how to find the volume of a prism. The volume of a prism is going to be length times width times height. So this is going to be our length, this is going to be our width, and then think about that after we fold it up. See how after I fold it up, what's going to be the height after it's folded? It's going to be x, isn't it? So let's go through this again. So the volume is going to be, what's this length here going to be? Right, so it's going to be 32 minus 2x. What's this width going to be? 32 minus 2x, the same thing. And then what did we just say the height's going to end up being? X. So this is our formula for volume. So now we have to multiply this all out. So I'm going to distribute this. 32 times 32 is 1024. The outers are negative 64x. The inners are negative 64x. Together that's negative 128x. The last times the last is plus 4x squared. I have to multiply that all by x. So when I do that, I'm going to get 1024x minus 128x squared plus 4x cubed. That expression represents our volume. If we want to maximize or minimize the volume, what do we do at this point? Take the derivative and set it equal to 0. So the derivative is 1024 minus 256x plus 12x squared. I'm going to have to set that equal to 0. So I have 12x squared minus 256x plus 1024 equals 0. These are some pretty big numbers to try to factor. So rather than trying to factor them as is, I'm going to think, can everything be divided by 12? Well, 1024 cannot be divided evenly by 12. So I know everything can be divided by 4 though, so I'm going to do that. I'm going to divide the whole equation by 4. 3x squared minus, what is that, 64 plus, dividing that by 4 is going to be 256. So this is a little bit easier to factor now. So I'm going to set up my double parentheses. I know it's going to have to be 3x and x. What are numbers that multiply to be 256? It's a perfect square. Do you know the numbers that multiply to be 256? Anybody know the square root of 256? 16. So 16 times 16 is 256. Check the outers, I get 48x. Check the inners, I get 16x. And I'm trying to get negative 64. So how can I get negative 64 with those two? What do I need the signs to be? They both have to be negative. So now solving this, I have 3x minus 16 equals 0, and x minus 16 equals 0. So when I solve this, I get 3x equals 16, x equals 16 thirds, which is 5 1/3. Here I get x equals 16. I got two answers. When I get two answers like that, what happens is one of these would result in a maximum and the other one in a minimum. Think about our square again. Our square was 32 by 32. We're cutting out certain sizes of squares. Can you think of which one of these could not maximize our volume? Who said that? Why, Michael? Why can't I use 16? Okay, watch what happens. I take my original thing here, and I cut out 16-inch squares. It was 32 to start with. Here's what I'm left with. Nothing. Everything's gone. I don't even have a shape anymore, right? Because it was 32 by 32. So this is going to result in a minimum volume of 0. That's certainly not the answer. So the answer is going to have to be this one. So we would cut out 5 1/3 inch by 5 1/3 inch. And that's going to give us our maximum volume. Now, let's say that you're not great at factoring. So maybe some of you, when you got to this part, you're thinking, I would not know how to factor that. A couple of things you could do. One thing I could do is I could put in this function, 3x squared minus 64x plus 256. I can put that into y sub 1, and into my y sub 2 I could put in 0. I can do a zoom standard. This is what I see. I'm not seeing the other part of it though, so I'm going to extend it down. I'm thinking about x representing the size of the squares that I can cut out. So I know it can't be any bigger. I would know it couldn't be any bigger. Let's say 32, because I would know that for sure. So here's what I have. So I'm trying to solve this equation. I know x can't be anything bigger than 32, so I have this. So now I can do second calculate, and I can find the point of intersection. So I'm just going to get close to that first answer. There it is. Oops, right there. So I'm going to push enter, enter, enter. And it tells me that it's 5 1/3. That's one thing that's going to make that equal 0. The other values, second trace, find that point of intersection. And you can also do this by finding the zeros. See, I'm looking here at y. I want y to be close to 0. Oops, a little too far. Enter, 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 and 16. So see how that can help me to solve that? Another thing I have on this calculator that's helpful is I have a program that I put in. It's a quadratic formula. Let me clear everything out. If you want this program, I could link up to you and you could get it, or you could put it in yourself. You could type it in under program. So I take this quadratic and the coefficient's 3. This coefficient is negative 64, and my constant's 256. And I get my two answers of 16 and 5 1/3. So lots of different ways we can solve that if we're not great at factoring these more complicated problems. All right, let's look at the second example. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1½ inches, and the margins on the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So we're going to draw a rectangle. We need to have 24 square inches of print. The margin at the top and bottom are 1½ inches. So I know this has to be, right here is 1.5. And I know down here has to be 1.5. The margins on the left and the right are to be 1 inch. So I know that this margin has to be 1 inch, and I know this margin has to be 1 inch. So I want all of this part, though, is where all the writing would be. And the question is, what should the dimensions of the page be so that we can meet all these requirements but use the least amount of paper? Well, what if I call this X right here? This is X, and this right here I'm going to call Y. What would I know about X times Y? What does X times Y have to be? How much printed part am I supposed to be using? 24, right? So I know this. I know that X times Y is going to have to be 24. Now, the area of the paper, the total piece of paper's area, that's what it is that I'm trying to minimize. Joe, can you think of what this would be right here? If this is X, and this is 1, and this is 1, what would this whole thing here be? If I've got X plus 1 more. And then what about this side? Matthew, what's this going to be? If this is Y, and I've got 1.5 and 1.5, what's this whole thing here going to be? So I'm trying to minimize the area of this whole sheet of paper here. So the area of this whole sheet of paper is going to be base times height, or length times width. I know I have to take the derivative of this, set it equal to 0, and solve, but what am I going to have to do first? Lizzie? Say it again? Okay, but I want to get rid of the Y first. How can I get rid of the Y? Stephen, do you know how I could get rid of the Y?
Put her on the other side or substitute it.
Okay, but and what could I substitute in? What does Y have to equal?
24 over X.
24 over X. That's the key right there. Because I only want to have Y's in this. So I'm going to have A equals X plus 2. Y is 24 over X plus 3. So now once I've done this replacement, now I have an area formula that only has X's in it. And so now I can distribute. So X times 24 over X is 24. That's going to be 3X. That's going to be 48 over X. And that's going to be 6. So my area is going to be 24 plus 6 is 30, plus 3X, plus, and then how can I rewrite that? So I can take, go ahead, Paige, what is it? Right. Because now I can take the derivative of it more easily. So I'm going to have A prime equals, that derivative is 0, that's 3. 48 times negative 1 is negative 48, x to the negative 2. Setting it equal to 0. I'm going to go back and call it this now. Bless you. Take this over. How do I solve something like this? Cross multiply. So I'm going to have 3x squared equals 48. X squared is 16. So x equals plus or minus 4. But I can't have a negative, so it's just going to have to be 4. Now, here's where people miss points, though, because that's not what the question's asking. It's not just asking us to solve for x. It says, what should the dimensions of the page be so that the least amount of paper is used? We want to know the dimensions here and here. Well, we should know this one because we know what x is. So what's the width going to be? The width is going to be 6 inches. And then the height of this, well, I have to know what y is first. Well, I know x times y is 24, and I know x is 4, so what's y? Y is going to be 6, and so what's this whole thing going to be then? It's going to be 9. So the height's going to be 9 inches. And so that's going to be the size of the paper that will do all of this. That's going to meet the restrictions on the margins, that's going to meet that requirement, and that's also going to minimize the amount of paper that's used. Guys, a lot of things in marketing, there are people who have to figure this kind of thing out. You know, a company comes somewhere to maybe an engineering firm, a marketing firm, something like that, and they would say things like this, like, we want to minimize our costs. How can we do that? But we still want to have our paper look good. We want to have these sizes of margins. Tell us how we can make this happen. And people do that. All right? Maybe you've noticed in a store, like if you buy a 6-pack of Coke, and that has maybe a price of $4.50. But if you buy a 2-liter, maybe that's close to the same amount of beverage, but it's only $1.99. Why is it that it's so much cheaper if you're actually getting more of the Coke? What might be at play there? Why, guys? Why does that happen? It happens all the time in everything you buy. Exactly, the packaging costs. That aluminum may actually cost more than the product that they're selling, okay? So sometimes those are all the kind of things that go into, you know, marketing. And then, like, why are things, you know, why do they use certain types of boxes too? Like, that's another thing that's important in marketing. Like, think of a cereal box. You know, a cereal box, like, it has that really big face, but then the width of it is very narrow. Why do you think that might be? Yeah, you don't really notice, oh gosh, there's really not that much in there. A lot of these things, like, there are mind tricks, you know. Like, even if they double the width of that, so you got a lot more cereal, it may not increase their sales because people really don't notice that. All they notice is that big front face, and they make it bright so that it catches your attention, you know. So there's just a lot of thought that goes into everything that we consume. All right, and all that's about optimization. So you guys have your assignment up there.